Ever stop and wonder how your phone can pick your face out of a photo? Or how a self-driving car knows a stop sign when it sees one? It really all boils down to one simple but incredibly hard problem. How do you teach a computer to see a shape? Well, we're about to dive into the amazing and kinda accidental math that finally gave computers their sight.
Okay, so here's the real puzzle. For you and me, right, a square is a square. Doesn't matter if it's tilted, upside down, whatever. But for a computer, every time you rotate that square, all the ones and zeros that describe it, they change completely. So how in the world does it know it's still looking at the exact same object? That was the big challenge.
And this slide really just lays it all out. On one side, you have the old way of doing things. You turn the shape, and its mathematical description just goes haywire. It's a totally different value. But then, on the other side, you have Zernike Moments. They create this stable, unique fingerprint for a shape, a value that stays the same, no matter how you spin.
So to really appreciate just how much of a breakthrough that fingerprint idea was, we have to go back and look at what was broken. Let's dig into the pretty serious flaws that plagued the first attempts to get computers to see shapes.
The old techniques, these things called geometric moments, they were a mess. They had this big technical problem: they weren't orthogonal. Now, all that really means is they were capturing tons of redundant, overlapping information, super inefficient. And like we said, they were terrible with rotation. Even a little bit of static or noise in the image could throw the whole calculation off. They just weren't reliable, and everyone knew a new approach was desperately needed.
And this is where the story takes a really cool turn. The answer didn't come from some computer scientist who was staring at pixels all day. Nope, it came from a totally different field, almost completely by accident.
The solution was actually hiding out in the world of optical physics. It was in the work of a Dutch physicist named Frits Zernike. And get this, he wasn't trying to teach computers how to see. He wasn't thinking about images at all. He was studying the fundamental properties of light passing through lenses.
The journey this idea took is just incredible. It starts way back in 1934, when Zernike created these special mathematical functions, called polynomials, to describe tiny imperfections in microscope lenses. He even won a Nobel Prize for related work in 1953. But his specific math just sat there in the world of optics for decades, until 1980.
That's when a researcher named M.R. Teague published this landmark paper. He's the one who finally connected the dots. Teague had this brilliant insight that Zernike's math, which was designed for light waves, could be adapted for image pixels to finally give computers that stable, rotation-proof vision they needed.
Okay, so how does this stuff actually work? The deep math can get pretty hairy, but the core idea behind it is actually beautiful and simple. Let's walk through a really basic example to see the magic for ourselves.
We're just going to use this tiny 5x5 grid of pixels. Right in the middle, we have our shape, a simple 3x3 square. So that's 9 pixels that are on and the rest are off. Our whole goal here is to create that unique signature for this little square.
And here is the secret sauce. This is the magic rule. Zernike Moments have this amazing property where they completely ignore any pixel that's outside of a specific circle drawn right around the center of the image. It's kind of like taking a circular cookie cutter to your image, and you only care about the dough that's left inside.
Now watch what happens when we use that cookie cutter on our 3x3 square. The 4 corner pixels, they're actually too far from the center. They fall outside the circle. And just like that, poof, they're gone. Our problem just got so much simpler. Instead of dealing with all 9 pixels, we only have to worry about the 5 that are left inside.
So here's the basic recipe. First, the computer finds the exact center of the image. Then it applies that unit circle rule we just talked about, tossing out any pixels on the outside. After that, it's actually pretty simple. It just adds up the values of the pixels that are left and then applies one final little tweak, a normalization factor, just to keep everything consistent. And here's the payoff. All of that process boils down to one single, elegant number: 5 divided by pi. This is the simplest possible Zernike moment. And what it represents is basically the average brightness of our shape inside that magic circle. This one number, this is the very beginning of our shape's unique fingerprint. Okay, so we have our number, 5 over pi. Big deal, right? Well, yeah, it was an absolutely massive deal. Let's look at why this simple idea was such a gigantic breakthrough and why these moments totally crushed the old methods.
The difference is just night and day. Remember all those problems we talked about at the start? Zernike Moments solved every single one of them. They got rid of all that redundant data. They finally gave us true rotation invariants. They were way better at handling noise, and they were an incredibly efficient way to describe a shape. It was a complete and total game changer.
So if you only take one thing away from this whole explainer, let it be this. Zernike Moments create a unique mathematical fingerprint for a shape. It's a signature that stays constant, giving computers a reliable, trustworthy way to know what they're looking at, no matter how it's turned or tilted. And that really leaves us with a fascinating thought to end on, doesn't it? An idea from 1930s optics solved a critical computer problem in the 1980s. It just makes you wonder, what other brilliant, decades-old ideas are out there, just hiding in some totally unrelated field, waiting for someone to connect the dots and solve the biggest challenges of tomorrow?
Welcome to The Explainer. Today, we're diving into some pretty brilliant math, the kind that lets computers actually see and understand shapes. We're going to see how it turns a really complex visual puzzle into a set of simple, elegant numbers. So, here's our game plan. First, we're going to look at a fundamental problem in computer vision. Then we'll get into the super clever solution. We'll even peek under the hood a bit to see how it all works, check out its real-world impact, and wrap up with a fascinating story of where it all came from.
Okay, let's jump right in. We're going to start with a question that, for us humans, is a total no-brainer, but for a computer, yeah, it's surprisingly tricky. You know, when you look at something, say your coffee mug, your brain just knows it's the same mug whether it's right side up, upside down, or you're looking at it from the side. But how on earth do you teach a computer to do that? How do you give it that basic, fundamental skill of recognition? Well, back in the day, say before the 1980s, the tools computers had for this were, well, they were kind of fragile. A simple thing like rotating an object would completely throw them off. They just couldn't handle the noisy, messy data you get in the real world. And on top of that, they were super inefficient, basically doing the same work over and over by capturing redundant information. And you can really see the problem when you lay it all out like this. These older methods like geometric or hue moments, they just weren't cutting it. See that part about being orthogonal? That's a fancy way of saying they were inefficient, capturing the same info multiple times. They couldn't handle rotation, and a little bit of visual noise would just wreck their results. It was obvious that something way, way better was needed.
And, well, that need for something better, it led to a genuine breakthrough, something that completely changed the game for computer vision.
This is it, Zernike Moments. Think of it like creating a unique mathematical fingerprint for any shape. It's like taking a complex object and boiling it down into a kind of shape DNA, a special set of numbers that's totally unique to that shape. And the best part? That fingerprint stays the same even if you spin the object around. That's the magic right there. So, Zernike Moments had these two superpowers that just crushed the problems we saw earlier. The first one, rotation invariance, means a letter A is still seen as an A even if it's upside down. And the second, orthogonality, means every piece of that mathematical fingerprint is one of a kind. No wasted effort, no redundant data. It just makes the whole thing so much more efficient and reliable. All right, so how does this magic trick actually work? Let's take a look inside. We're going to walk through the main idea, but don't worry, we'll skip the scary math. And it's actually a pretty logical process. First, the computer finds the dead center of the shape. Easy enough. Then, it draws this imaginary unit circle around that center point, and basically ignores anything outside of it. This just makes sure every shape is measured on the same playing field. After that, it applies a special mathematical filter. That's the Zernike polynomial, to the pixels inside the circle. And finally, it just adds up all those results and tidies them up to create one single, powerful number. That's it. That's one Zernike moment. Let's make this real. Imagine a super simple shape made of, say, 9 pixels. Because of that unit circle rule, maybe only 5 of those pixels actually count. So when the math is all done, the very first, most fundamental Zernike moment, we call it Z00, ends up being just 5 divided by pi. That's it. All that visual information gets distilled down into one simple, elegant number. Okay, so we've got a handle on what this is and kind of how it works. Now for the really cool part. Let's look at where this mathematical fingerprint is making a huge impact out in the real world. And wow, the list is seriously diverse. We're talking about the math that helps doctors spot cancer cells just by their shape. It's what's behind the facial recognition on your phone. It's used in OCR to scan old books, on factory floors to catch tiny defects, and even in space to analyze images from satellites. It's everywhere.
And this isn't just for everyday tech. We're talking about the highest levels of science here. This is the exact math NASA relies on to calibrate their incredibly powerful telescopes. It's what ensures those stunning images of the universe are perfectly sharp and clear. So yeah, this is a pretty big deal.
So, who came up with this brilliant idea? The backstory is actually fascinating, and it starts way before anyone was even thinking about computers seeing things.
So check out this journey. It all starts back in 1934 with a physicist named Fritz Zernike. He wasn't thinking about images at all. He developed these special polynomials for his work in optics, and he ended up winning a Nobel Prize for it. But here's the crazy part. It took nearly 50 years until 1980 for another researcher, M.R. Teague, to have that aha moment and realize, hey, we can use this math for analyzing images. And just like that, Zernike Moments were born.
But, nothing's perfect, right? To get this kind of amazing accuracy, it does take some serious number crunching. Calculating all those different moments can be pretty intensive for a computer, and they really need a clean image to work with. If the object isn't clearly separated from the background, the results can get a little messy. So getting that perfect silhouette is super important.
So this all leaves us with a pretty cool thought. Zernike Moments are just this perfect example of how some really abstract, Nobel Prize-winning math from a completely different field can suddenly become this foundational tool for our modern world. It's the hidden engine that's quietly helping machines make sense of what they see. It really makes you wonder, right? What other invisible math is out there just waiting for someone to find a brand new way to use it?
All right, let's dive right into something that sounds super complicated, but is actually pretty cool when you break it down. We're going to take this simple grid of pixels and step by step turn it into one single powerful number. We are calculating a Zernike moment, and trust me, by the end of this, you'll see exactly how this helps a computer understand a shape. Let's get to it.
So think about this for a second. Let's say you're trying to get a computer to recognize the letter A. Seems easy, right? But what happens when that A is tilted sideways or completely upside down? All of a sudden, it's a totally different problem. How can a computer possibly describe a shape in a way that its orientation just doesn't matter?
Well, the answer is these things called Zernike moments. The best way to think about them is like a unique mathematical fingerprint for any given shape. And their absolute superpower is that this fingerprint stays exactly the same no matter how you spin that shape around. That's what we mean by rotation-invariant. To really see how this magic works, we're going to calculate the most basic Zernike moment. It's called Z00 for this very simple 5x5 image. As you can see, we've got a little 3x3 square of ones right in the middle, which gives us 9 active pixels to work with. But as you're about to find out, not all of them are actually going to make the final cut.
Okay, first things first. We have to find the image's center. See, if we want to create a description that doesn't care about rotation, we absolutely need a stable pivot point, a central anchor. This is a crucial first step because literally everything else we're about to do depends on it.
And luckily, for a square image of size n, the formula for this is beautifully simple. You just take the dimension, n, subtract 1 from it, and then divide the whole thing by 2. That gives you the coordinate for the center.
So for our 5x5 image, n is 5, right? So 5 minus 1 is 4, and 4 divided by 2 is 2. That tells us our center point is at the pixel coordinate 2, 2, assuming we start counting our rows and columns from 0. It's the dead center of our grid.
Now for a really interesting part, we're going to shift our entire frame of reference. We recalculate the coordinates for each of our 9 active pixels by subtracting that center point from them. So the pixel that was at 2, 2 now becomes our new origin, 0, 0. This recentering is so important because it makes our final description independent of where the shape was located in the first place.
And now for our second major step, applying something called the unit circle. This is where things get really fascinating. Zernike moments are actually only defined inside the circle, so it basically acts like a filter or a gatekeeper. This standardizes the whole analysis, making sure we're always looking at the exact same sized area. And as we're about to see, some of our pixels are not going to get past it.
The rule itself is pretty straightforward. For a pixel to be included in our calculation, its new centered coordinates, x and y, have to satisfy this simple equation. X squared plus y squared must be less than or equal to 1. If that looks familiar, it's because it's just the standard equation for a circle that has a radius of 1. So let's put our pixels to the test. Take a pixel at -1, 0. That gives us -1 squared, which is 1, plus 0 squared, which is 1. That's less than or equal to 1. So it's in. But now look at a corner pixel, like -1, -1. That gives us 1 plus 1, which equals 2. That's bigger than 1, so it's out. As you can see, all 4 of our corner pixels fail this test.
And just like that, our 9 active pixels have been whittled down to just 5. These 5 pixels, the ones that form that plus sign shape, are the only ones that actually matter for our calculation from here on out. This filtering is a really fundamental part of how Zernike moments work.
All right, time for step 3, the polynomials. Now this is the part that often looks really intimidating, with all its crazy math symbols. But I promise you, for our specific case, the math turns out to be shockingly simple.
So this is the general formula for what's known as the radial polynomial. Yeah, it looks like a mess, right? Summations, factorials, variables all over the place. This thing is powerful enough to handle any Zernike moment you can throw at it. But for what we're doing today, it's total overkill.
Now, just watch what happens when we use this formula for our simple case, where the order n is 0 and the repetition m is also 0. The moment you plug those numbers in, something kind of magical happens. The entire complex structure just collapses.
It simplifies all the way down to the number 1. That's it. The entire scary-looking polynomial for our specific z00 moment is just 1. It doesn't even matter which pixel you're looking at. So for every single one of our 5 valid pixels, this value is just 1.
You know what? We've basically done all the hard work. We found our center, we filtered our pixels, and we figured out our polynomial. Now it is time to put it all together and get the final answer. The final calculation is just a simple 2-step process. First, we're going to sum up the intensities of our valid pixels. And second, we multiply that sum by a little something called a normalization factor to get the final moment.
So, remember those 5 pixels that passed our unit circle test? Each one has an intensity value of 1. All we do is add them up. 1 plus 1 plus 1 plus 1 plus 1 gives us a grand total of 5. Easy enough. And for the final step, we apply that normalization factor. For a moment of order n equals 0, the factor is simply 1 over pi. So, we take our sum, which was 5, we multiply it, and there it is. The Zernike moment z00 for our little image is 5 over pi.
So what does 5 over pi actually mean? Well, this specific moment, 0, 0, 0, represents the average intensity of the image inside that unit circle we used. You can just think of it as a measure of the shape's overall brightness or its mass in that central region. And that kind of leads us to a final, bigger question. We just calculated the simplest possible moment, one that basically captures brightness. But what happens when you calculate z11 or z53? What kinds of complex details about a shape's edges, its asymmetry, or other fine features do those higher-order moments allow a computer to finally see? Well, that's where the true power of this technique really begins to unfold.